Okay, in this video, what I plan on doing is I plan on solving the three problems that were due at the middle of the week with respect to Exergy. I'm using a new software package called Screencast, and so hopefully this will be a little bit more, you'd have a little bit more utility than using Collaborate. You also can have my picture off to the corner there if you're so interested in that. So the first problem that we're going to solve is problem number 619, ONV. And in this particular case, we have a rigid tank containing 20 kilograms of liquid water at a pressure of 100 kPa and at a temperature of 25. Obviously, at those pressures and temperatures, we do know that steam in the form of liquid water would be the preferred phase. And so we are told that this rigid tank obtains heat at a given rate at 10 kilowatts or 10 kilojoules per second. That's what's transferred into the tank, and it's transferred from a source temperature of 1000 Kelvin. Okay, and so we're to determine the rate of energy transfer from the heating source. Okay, so that will just be exergy due to heat transfer. And then while we're at it, we want to determine the rate of increase of temperature during a process. Now, in this particular case, you are told that 10 kilowatts per second, or excuse me, 10 kilowatts is the rate of heat transfer. Now, 10 kilowatts is just 10 kilojoules per second. And so, in essence, when they're asking for the rate of increase in temperature, we are just looking for what can 10 kilojoules do to the 20 kilograms of water on a per second basis. And so if we know the specific heat of the water, we know how many degrees of temperature it will rise for every kilojoule of heat per kilogram. And so the second part is really just a first law problem with an increase in temperature. And then we're also looking for the rate of exergy change of the water in the tank. And so that's going to be looking at the value of phi and how phi is increasing with respect to time. And so we'll look at this problem first. In this particular problem, when I pull up the test software and I go to the test app, this is just a closed system, a simple process, and the fluid in question, as we can see, because we're dealing with just liquid water, we can go ahead and select the solid liquid model. Okay, it is going to be, for the case in hand, we are going to be looking at just the effect on liquid water. Now, if we allowed it to continue for a long period of time, eventually it would go into the phase change model. So for the solid liquid model app, we see that we have our state panel. Since we are including exergy in this particular case, we can go to state 0. And in this particular problem, we are told that the atmospheric temperature is 298, and so we can put that in terms of Kelvin. 298, that's the dead state temperature. And we also know that the pressure, we can assume the pressure is just 100 kPa. We don't know what it is, but that's a good atmospheric pressure to use for the dead state. And so we've determined we've determined the dead state, and now when we go to state 1, what do we know about state 1 is that we have 20 kilograms of water. Now that 20 kilograms of water, liquid water, because water is incompressible, we know that the density is going to be relatively constant, and we start the system at 25 degrees Celsius. And we also say that it's at a pressure of 100 kPa. And so with this in mind, our liquid water, 20 kilograms of the liquid water occupies this volume. If I were to switch that over to liters, it's about 20 liters of water. And we see that the enthalpy, the internal energy, and everything is calculated. We also observe that the magnitude of the phi, or the exergy, at that particular state. And in this particular case, that state is very close to the dead state. It's only 25 degrees, and we had said the dead state was 298, which is just a little bit below that. So if I were to switch this over to Kelvin, we're actually looking at just 0.15 degrees above the dead state. And so therefore there's a slight amount of exergy for the liquid water at this condition. Okay, with that known, then we can go to the process panel, or better yet, we can go to state 2. Now, what do we know about state 2? We know that state 2 has the same mass as state 1. It also, will have the same volume, but we know that the temperature at this particular case is going to go up, and it's because the internal energy of this closed system has increased. Now, how much has this internal energy gone up? Well, we know that it starts at U1, and then because we know that the heat transfer rate is 10 kilojoules per second, if we want to know how much the internal energy changes in 1 second, and that's what we're going to say state 2 is how much has the internal energy changed for 1 second, we know that the increase in internal energy is just going to be 10 kilowatts per second divided by the mass, because 10 kilojoules per second divided by the mass of 20 kilograms then is how many kilojoules per kilogram rise in internal energy there is per second. And so when I do the 10 divided by 20, every second the specific internal energy is going up by a half, 0.5. Okay, now with that known, we see that the temperature does go up to 25.1195. Now in this particular case, because we need that pressure to calculate all the rest of the properties, I can put in this, I can say that it's at the same pressure. And so what we see now is we've actually determined for this particular problem the answer to part 2. And the answer to part 2 was how much, or what is the rate of temperature increase at every second due to that heat transfer rate. And what we see is it went from 25 to 25.12. So the answer to 2 decimal places is just 0.12 degrees Celsius. So every second it would go up that amount. We can also answer the question that we had before, or also the third question is how much is the exergy within the system increasing? And so the exergy starts at this 000157 and it goes up to 000509. And so the difference in those two values of phi on a per mass basis, if I then take that difference and multiply it by the mass, because we have a certain mass in this system, we can actually determine how many kilojoules of exergy per time, actually was increased. So if I go to my process panel, in this particular case, what I do know, if I look at my energy equation, there is no work that's been done on that water inside that rigid tank. And so there's no electrical work, there's no shaft work, and there's no boundary work. And so this whole combination of external, I can say that the boundary work is equal to 0. Okay. Now, what else do I know in this particular case is that I recognize that for this closed system, there was, let's see, okay, we do know that the heat transfer that does occur is coming in at a boundary temperature of 1,000 Kelvin. So I need to change this over to 1,000 Kelvin. And so if I did, let's see, I know that the heat transfer is equal to, now here's how much heat transfer occurs as I go from state 1 to state 2. Now, what I forgot to do was to actually indicate that state 1 and state 2 are the incoming and the outgoing. So if I turn that off and I just say that the before state is 1 and the after state is 2, and I select this right here along with that temperature, I can now do a calculate, and it calculates based on what I had put in for the change of internal energy. It calculated that the heat transfer per second was 10 kilojoules per second. Again, keep in mind that state 1 to state 2 was done over 1 second. And so what else is in this? We know here this is the change of the exergy of the system on a per 1 second basis. And so it was 0.007. Okay. Again, that's the phi difference, and we know that that phi difference occurs for 20 kilograms, and so that then gives us the kilojoules, and we know that this is for 1 second. And so we've answered that question. Now, what we haven't answered was how much exergy was transferred in, the rate of exergy transferred in due to the 10 kilowatts, and we see that it's calculated right here. Excuse me, it's calculated right here. It is the phi change due to heat transfer. And so for this particular process of 1, it is this value right here. And so that would actually just be equal to the 10 kilowatts times the 1 minus T0 over 1,000. Okay, so we had to put in this boundary temperature. If the problem had said that the boundary temperature was at 500, then, and if I do a recalculate here, you see that that number changes because 1 minus 300 approximately over 500, that is the multiplier for the 10 kilowatts to give us how much exergy came in due to heat transfer. And so in essence then, if I go back to this particular 1,000, put in the right number here, okay, the answer to our problems, now I can go to the I.O. panel, I can do a super calculate, I can go back to the process panel, and the answers to the questions that I'm looking for in this is the exergy transfer due to heat at the 1,000. And again, this would be in kilojoules per second, okay, kilowatts. And then this is the change in the stored exergy value. Again, this would be in kilojoules per second, kilowatts. And then finally, we were asked to determine how much the temperature went up. And the temperature goes up here by the difference between this temperature and the previous temperature. And so if I were to go back to state 1, put it into Celsius, that's 25, and it's 25.12. So that's the answer to the rise in the temperature. Okay, with that, we're going to shut that down.